Okay, continuing on in Unit 6, we're going to talk about the last type of biological molecule, proteins. And so you've probably heard of proteins. Proteins are discussed a lot regarding diet and bodybuilding and all of that. Proteins are made up of many amino acids, and they're linked together by peptide bonds. So to understand more about proteins, we have to find out what an amino acid is. And if you remember from organic chemistry, units 3 and 4, we talked about the amino group, and we also talked about acid, carboxylic acid group. So an amino acid has the functional group, has an amino, so the amino looks like this, and then it has a carboxylic acid. So the way these are assembled to make up an amino acid, you have the amino group here, then you have a carbon, then you have the carboxylic acid. So you have amino, carbon, carboxylic acid. If you look at this central carbon, I only have 3 bonds drawn to it. There should be another bond, and there is another bond coming off. That's referred to as the R group. This varies for each amino acid. There are 20 amino acids that are used by humans to make proteins, and so that's not very much variation. But if you think about it, humans have millions of proteins with different functions and different structures. So, but it only takes 20 different building blocks to give all this variety. So the R group we're going to talk about coming up later on. It can be a hydrogen, it can be a methyl group, it can be an isopropyl group. It just depends on the amino acid. So we've learned so far that proteins are made up of amino acids. We've learned the amino acid structure. Now we're going to learn about the peptide bonds. So a peptide bond is something you already know. You learned it in Unit 4. It's an amide bond. So remember that an amide is a carbonyl connected to a nitrogen. So that is an amide. Now, you could probably tell me, since you've been studying so hard for your final that's coming up, how to make an amide, right? Sure. Everybody's writing it out now. So to make an amide, you take a carboxylic acid, plus an amine, and remember that you get rid of water. You take off the OH here, take off the one of the H's here, make a really long bond, and that's how you come up with an amide. Looks like an L, but it should be a C. So your other product would be water. So if you look at the structure of an amino acid, you have the carboxylic acid and you have an amino group. So you have the components necessary in an amino acid to make up an amide or peptide bond. So what happens, and this is how proteins are built, is that amino acids can form amide or peptide bonds. So they can be linked together, and you can just imagine thousands of these amino acids linking together to form a very complex protein. So if you look on the next page, two or more amino acids can link together to form a peptide bond. I have two amino acids here. You know they're amino acids because they have the amine carbon carboxylic acid. So the R groups are here. So these amino acids, based on their R groups, are called valine and cysteine. You don't need to know the names and the R groups, but just to show you that the R groups determine the amino acid's name. Now, valine and cysteine can be linked together by a peptide bond. The way you would show this, and you need to know how to do this, is by losing OH here, losing H here, making a really long bond. And the only thing that changes is the carboxylic acid and the amine, where they've joined together. So you're just going to copy these down. So the R group hasn't changed. Get to the carbonyl. Now, at this point, instead of an OH, we'll have an NH. And then we'll link that to the other amino acid, cysteine. So that's how you would show two amino acids forming a peptide bond. This is the peptide bond. Another thing I want to point out about these amino acids linking together, we're going to talk about this a little later, but if you've seen the book, sometimes you'll have the OH without an H and it will be minus, or the NH2 will be NH3. So I'll write this. Sometimes you can see it as NH3 plus or O minus. And we'll talk about that a little bit later on, but either one is acceptable. Now, we're going to talk about the different classes of amino acids, and the classes are based on their R groups. So I recommend writing the general structure of the amino acid. Now, you should know how to write the general structure of the amino acid, but you don't have to memorize the R groups in the names. So, and I'll clarify this more as we go on. So the general structure of an amino acid, you have your amino group here, carbon with a hydrogen, carboxylic acid, OH, and then you have your R group. So we're going to go through the nonpolar amino acids first. So nonpolar groups, these are going to be, they don't want to mix with water. So won't mix with water. So the first nonpolar R group is for glycine, and this one is just a hydrogen where the R is. The next one is alanine, and alanine has a CH3. Valine has an isopropyl group, so it's CH, CH3, CH3. Isoleucine has a sec-butyl group. And again, you don't have to memorize these. We're just going to look at the general trend and what we see with nonpolar R groups. Leucine is an isobutyl group. Methionine is CH2, CH2, S, CH3, and then phenylalanine is CH2 with a benzene ring. Now, I I don't want you to memorize the R groups and the names of the amino acids. What I do want you to know is that nonpolar R groups, what do they have in common? So you can generalize. So nonpolar R groups, with the exception of glycine, all have carbons. Lots of carbons. So, and I'll put exception H for glycine. Okay. Now, you probably have come across this term, phenylketonuria, or PKU. This is where you cannot metabolize phenylalanine, the amino acid phenylalanine. And so, people who have PKU, if they do ingest phenylalanine, can develop a mental retardation. They tend to be very mean. But if you have a family history of PKU, then you're aware of it and on the lookout for it. Newborn babies are screened for this in Kansas. I had a student who had a friend who had PKU, and she said that he was, very normal. He just knew not to eat certain things, and so he had to avoid different types of meats. And but one thing in particular that he had to avoid was diet sodas. So if you look at diet sodas, they say contains phenylalanine, phenylketonurics, beware. So if you have PKU, you cannot consume any diet sodas or anything that contains NutraSweet. So, because NutraSweet contains phenylalanine. So, moving on, the next class of amino acid R groups we're going to look at are the polar groups, and the R groups here. So remember, polar is likely to mix with water. So this mixes with water. So serine is CH2OH. Threonine is CHOH, CH3. Asparagine, shouldn't be an S on there. CH2, C double bond O, NH2. Cysteine, CH2, SH. Tyrosine, CH2. And then phenol, para. And then glutamine, CH2, CH2, and C double bond O, NH2. So what can we generalize about polar groups, polar amino acids? So there are groups. They have what in common? Well, they have alcohols, amides, alcohols. So if you look at your periodic table, alcohol has the OH functionality. So oxygen, and then if you look underneath oxygen, in the same group is sulfur. So OH is going to behave a lot like SH. That's the periodic law that we learned about way back when. So what you need to know, polar amino acids have alcohol functional groups, amide functional groups, and SH is called diol. You remember from Unit 4. So again, you don't have to know the names and the structures, just the general trend that's observed for the group of amino acids, or the classification of amino acids. Okay, the next class of amino acids we're going to learn are acidic groups. So aspartic acid looks like this, CH2, C double bond O, OH. So this is where the R is on the amino acid, so the side chain, it's another term. And then glutamic acid just has one more CH2. So there are only two acidic groups, for the amino acids. And what do you notice about acidic groups? They both contain carboxylic acid. So acidic groups contain carboxylic acids. Okay. The last classification of amino acids are the basic groups. There's just one. And it's called lysine. Not that you need to know the name or the exact structure, but it has 4 CH2s and then an NH2. And what we learned about in Unit 5 is that amines, which lysine has, are weak bases. So basic groups contain amines. So I want to be very clear. You will not need to learn the names or structures of the individual amino acids. This is what you need to know how to do. You will need to know how to write the general structural formula of an amino acid given the R group. So we will always provide the R group for you. The other thing you'll need to do for this section is to be able to classify the amino acid as polar, nonpolar, basic, or acidic based on the R group. And again, the R group will be provided for you. So on the next page, I want you to draw the structure of asparagine. And I'm just going to go ahead and give you the R group so you don't have to flip back. The R group for asparagine is CH2, C double bond O, and H2. So I want you to draw the structure of asparagine and classify it. I also want you to do the same for tyrosine. And tyrosine has the R group. Looks like this. And then lastly, I want you to draw the structure of the dipeptide bond formed between the following amino acids. So we're just going to link these two amino acids by an amide bond, being sure to write the correct product. So hit pause and do those things. Okay, so the structure of asparagine, you need to include the general structure of the amino acid. So if you just rewrote the R group, that's not enough. You need to include everything here and then plug in the R group. Now, here's a cat. Now, with these amino acids and protein structures in general, the nitrogen is written on the left and the carboxylic acid is written on the right. So that's how I typically write everything. So amino on the left, carboxylic acid on the right. So asparagine, I have drawn the structure for you here. The classification would be polar. So it's a polar R group. Now tyrosine, the only thing that differs is that instead of the amide that you had for asparagine, you just have the phenol. So tyrosine is polar as well. So make sure you know the general structure of the amino acid, because you will definitely need to know how to do that. And the last question, draw the structure of the dipeptide bond formed between the following amino acids. Circle the peptide bond. So you're just linking these together, making an amide. The peptide bond is right here. And at the dipeptide, if that threw you off, that just means you have two amino acids linked together. So two amino acids. And they're held together by a peptide bond, so dipeptide. If you had a tripeptide bond, or tripeptide, it would be 3 amino acids. So practice, practice, practice. Again, don't freak out. You don't need to memorize all the amino acids names and their R groups. That's way too much. So keep it simple. Moving on. We're going to talk about what happens when you put amino acids in solution. So let's just draw the structure of alanine. So alanine is an amino acid. I've given you the R group. This is where it really, really pays to know the general structure of your amino acid. And again, you will need to know this. So amino, the general structure of an amino acid. So you write your amino on the left. And there's a carbon in between that has a hydrogen. And then the carboxylic acid. And you plug in your R group, which for alanine is CH3, so you plug it in here. So amino acids ionize in solution. Ionize? That term is so Unit 5, right? You guys have probably forgotten it or trying to forget it. Don't want to think about what ionize means. Remember that ionize means to form charges. So amino acids ionize in solution. So let's look at alanine and see what could form a charge. Well, we have an amino group and we have a carboxylic acid group. What do you remember about amines from Unit 5? Again, I'm asking you to remember. Amines are mean and greedy. What do they want to take? They want to take protons. So they're greedy. They want protons. So we just talked about amines. If you look at the other side of this amino acid, we have an acid that has exactly what a mean and greedy amine wants. So this has a proton. The proton, which is up for grabs. So the way amino acids ionize in solution, it's just an acid-base reaction. The amine takes the proton from the carboxylic acid, so you end up with NH. Instead, not NH2, it's NH3, the plus, CH, CH3. Then the carboxylic acid has lost its proton, so it has a negative. So this is what I mean when I say amino acids ionize in solution. This is called a zwitterion. So it means hybrid ion, or double ion, because it has a positive and negative charges at the same time. So when you put amino acids in solution, this is how they exist. You're not going to see them in their neutral form. They don't exist like this. So this is how they exist in solution. So if you remember back to, there was a problem that it was at the top of page 12, where I said you could see NH3 plus or O minus. If that's in solution, that's more likely how it's going to be. So, be familiar with both, but more likely to exist in solution is the zwitterion, because amino acids ionize in solution. Now, let's talk about the isoelectric point. The isoelectric point is the point, or pH, at which an amino acid forms a zwitterion. So if you look at a zwitterion, overall, for alanine, for instance, plus, you have a plus charge and you have a negative charge. Overall, it's neutral. So the isoelectric point varies for each amino acid. Some amino acids are very acidic, so their isoelectric point is going to be a lot lower. Some are basic, it's going to be, the isoelectric point will be a lot higher. The nice thing about the isoelectric point is that you can separate amino acids based on different isoelectric points. So there's a whole area of, biochemistry, electrophoresis, and you can chop up proteins and then separate the amino acids and figure out how this protein is connected. And it's a very, very neat area of biochemistry, because you really have to work it as a puzzle. So it's trying to figure out, well, how does this piece fit together if I know I have these pieces. But the premise for all this, the electrophoresis, the separation of these amino acids, is based on the fact that each amino acid has a different isoelectric point. So you can separate them out. If they all had the same isoelectric point, it would be very difficult to separate them out, and you couldn't analyze them any further. So we will stop here for this lecture. We've talked about a lot regarding amino acids and proteins. We've talked mainly about the building blocks of proteins and how they link together. But study Unit 6. I know a lot of you think, oh, this is so easy. There's not any math. It's not really any nomenclature. I'm just going to blow this off. Please don't blow off Unit 6. I hope every one of you gets 100 on Unit 6, because compared to our other units, this is not as challenging as, whatever was most difficult for you. It's just straightforward, kind of, this is how it is. So make sure you spend some time on Unit 6. Do the final review packet. Do your pink book on Unit 6. Practice. There are too many students that I've seen in the past that blew off Unit 6, and Unit 6 can really help your grade. So study. So, until next time.